Alright, welcome back again. We'll continue our problem solving regarding the horizontal acceleration or the relative equilibrium. Okay, so we have solved this this delta H as 1.22 meters, and this diameter is actually given, which is I think this is 1.5 meters. Okay, and if we solve for let's say solving for pressure pressure on the rear wall, you will have this equation. Pressure is just equal to the okay, so this is the pressure P sub R. That's the pressure at the bottom minus the pressure at the top, and since we are considering only the gauge pressure, since this will be our reference line, then the pressure at this point would be 0, and that's why this is simplified. So this is the unit weight times the height from this point to the centroid, right? So recall this equation on forces on submerged bodies. Okay, so this is our working equation for the pressure. Okay, so if we solve now, the unit weight is just simply 0.82 times in 9.81, that's in kilonewton per meter cube, times the average height or the vertical distance from this point to the centroid. Okay, so this is the centroid of the surface or the rear wall. So this distance would be 1.22 plus half of 1.5. That's just 1.97, okay, right? So 1.97 meters. That's our H. Let's say H sub R. So 1.97 meters. Now, if you do the math, you would get 15.85 kPa. Okay, now since you have already obtained the pressure, then you can solve for the forces. Okay, so force is just simply pressure times the area. Okay, so force on the rear wall is just simply the pressure at the rear wall times the area of the rear wall, which is just pi d squared all over 4. So 15.85 kPa times pi d squared. The diameter is 1.5 meters squared all over 4, and that's 28 kilonewton. Okay, so the next step is to solve for the forces along the front wall, or on the front wall. Okay, so let's write this is number 6, step number 6, and we'll write solving for pressure on the front wall. Okay, so again, that's just the same procedure. So P sub F, that's pressure on the front wall, is equal to the unit weight times the height, of course, the equivalent height on the front wall. Okay, so if we refer back to this figure, this height would be, of course, just the half of 1.5, which is 0.75 meters. Okay, so this is our h bar sub f. Okay, so let's substitute all the values. 0.82 times 9.81 times 0.75 meters. Okay, and we get a value of 6.03 kPa, and therefore the force acting on the front wall is just equal to the pressure times the area. So that's 6.03 kPa times pi times 1.5 squared all over 4, and we get a value of 10.66 kilonewtons. Alright, now if we review our procedure, this is our problem. It says it is a closed horizontal cylinder. So the geometry is a cylinder, and what's given is the diameter, the length, and then the acceleration. And it says that it is completely filled with a gasoline. So in other words, the initial position of the free surface is at the top portion. Okay, so it says that it is accelerated horizontally at 3 meters per second, and we are asked to find the total force acting on the front wall. So what's the force on this front wall, and what's the force on this rear wall? Okay, so first what we did is, since we are given the value of acceleration, then we can use this relationship that the tangent theta is just equal to ax all over g. So we first solve that to find the inclined angle, and then we sketch the given so that we can visualize which unknown can be solved directly or something. And then since here we have drawn that we have the tilt angle, we have the delta x, then we can find for the delta h, because this is the key. Because once we've solved for the height here, then we can solve for the pressure. We solve for the pressure, then we can solve for the force. Okay, so we determined the height, and we got a 1.22 meters. Again, we made a sketch so that we can actually input the value of the effective height, or the mean height, the h bar. Okay, so from geometry, then we found out that it's 1.97. So that's the height from this free surface to the centroid, of the area that is concerned. Okay, so we solve for the pressure, and then we solve for the force. And the same thing that we did for the front wall. Okay, so we solve for the pressure, then we solve for the force. Okay, so that's so far what we have for this horizontal acceleration. And there can be many other types of problems, like for example, you have an open top, and then maybe you would be asked to what would be the limiting value for the acceleration so that it will not spill over. Okay, so that's possible, but then the basic principle still lies in the basic equations that we have, or the derived equations that we have for the horizontal accelerations. Okay, so now let's try to derive the equations. What if we have an acceleration, but it's along the vertical direction? So let's write it here. Acceleration along the vertical direction. Right, so we'll try to draw first the container. So this is our container or vessel, and it's filled with liquid, and we have this acceleration along the y direction. Okay, so it's accelerating upward. So it is also possible that it's accelerating downward, or decelerating upward, or decelerating downward. So that would just be a matter of the sign. Okay, so now let's consider an infinitesimal volume. Okay, so let's consider an infinitesimal volume right here. Okay, so the situation is that if it's not accelerating, then we have this level, right? We have this initial level. If it's accelerating upward, it's actually going to maintain the same level. Okay, so it's not going to tilt at an angle. It's simply because the acceleration is vertical. It's not horizontal acceleration, so it will just be the same. Okay, so let's consider this infinitesimal volume. Okay, so if we zoom this in, what we get is this volume. Now let's say this is our x direction and this is our y direction. Okay, so if we translate the coordinate system, this will be our x, this will be our y. Okay, and then if we expose the forces, then we have a forces from the pressure on top, and we have also forces along the at the bottom face. Let's say this is p sub y, because this is our origin, and therefore this one will be py plus delta y. Okay, and what else? We have another force coming from the body force, which is just the weight mg. Okay, so now let's try to apply the equilibrium equation. Okay, so summation of forces along the y-axis, that's going to be m times the acceleration. Okay, so again, it's not zero. It's simply because it is having a motion, and the motion it's actually having an acceleration. Okay, to be more precise, it's more on the acceleration rather than motion. Why? It's because you can also have an equilibrium condition, the summation of forces that's equal to zero, if you have a constant velocity, because if you recall that a is delta v all over delta t. So if you have a constant velocity, this one would be zero, and therefore a would be zero. In that case, that's going to be an equilibrium condition. Okay, so for this one, let's write it here. Summation of forces y is equal to ma. Now let's try to draw the three-dimensional view. And if this is our origin, then this will be our x, this will be our y, and then this will be our z. And therefore, the area concerned is, right, this is delta x direction, and then this one is delta z direction. Therefore, area is just simply delta x times delta z. Okay, so the force here is we have to multiply that by the area, right? So now let's write the equations here. the summation of forces y, and let's assume that the upward is positive, so anything that's going downward would be negative. Okay, so py times the area, and the area is just simply delta x times delta z, okay, minus this one, minus py plus delta y times delta x times delta z, minus this force mg is equal to mass times the acceleration along the y, the acceleration along the y direction. By the way, this is positive because if it is accelerating, then it will be positive. If it is decelerating, meaning it is, or in other words, it is slowing down, then this will be negative. Okay, so now let's express the mass. Okay, recall that mass is just simply the density times the volume, and the volume is just simply delta x times delta y times delta z. Okay, so py times delta x times delta z minus py plus delta y times delta x times delta z minus rho, the mass density, rho times the volume, which is delta x delta y delta z, times the gravitational acceleration, is equal to, again, mass, which is just rho times delta x delta y delta z, times the acceleration along the y direction. Okay, so since we have delta x delta z, right, delta x delta z, delta x delta z, delta x delta z, delta x delta z, then what we get is, okay, let's simplify the terms, py minus py plus delta y minus rho delta y times g, and this one rho delta y times a y. Okay, so let's simplify further. Let's retain the pressure in this left hand side, and then this term will transpose this to the right hand side. So py minus py plus delta y is just rho delta y times ay, okay, plus rho delta y times, okay, times g. Okay, so what is this rho g? Okay, so rho g, that's just simply the unit weight. Okay, so let's write this is delta p equal to rho g, the unit weight, okay, times delta y. Okay, so the same hydrostatic equation plus this term right here. So we have the rho times the acceleration on the y times the delta y. Okay, so basically what this means is that the pressure variation is just, or the pressure difference would be the hydrostatic equations plus some values. Okay, these values. Okay, so if we check the units, this one is in pascals, right? That's in Newton per meter squared, and then this is kilogram per meter cube times the acceleration, which is meter per second squared, times the height, the length unit. So this is Newton. Okay, so Newton, and then meter cube divided by meter, so that's Newton per meter squared. Now if we rearrange this, we can also arrive to this expression. Okay, so delta y times 1 plus ay all over g. Okay, so it means that this is our pressure equation, or pressure variation equation, if we have an acceleration along the vertical direction. Okay, and the increase in pressure is given in this term right here. Okay, so the hydrostatic plus the term right here. Okay, so let's talk about the plus and minus. Now, if we have in this sign right here, this can be actually plus or minus. So this one is plus if it is going upward, or minus if it is going downward. And this one, this can be plus or minus. It is plus if it is accelerating, and it is minus if it is decelerating. Okay. Okay, so now we'll try to sum the forces along the x direction, and in the x direction we would see that there is no pressure difference. Okay, so summation of forces x 0, then it just means that p x would just be equal to p x plus delta x. So the pressure acting on this side is just equal to the pressure acting on this side. Okay, so now let's try to apply this equation in one of our problem. Okay, so problem 4.2. The problem says an open tank containing water is accelerated vertically at 6 meters per second squared. And the tank is 0.5 meters in diameter and 1 meter in height. The water is filled up to a depth of 0.8 meters. Determine the pressure at the bottom of the tank. Okay, so since we're not given with any figures or illustration, then the first thing to do is to sketch the problem. Okay, so the problem says we have this tank, an open tank, and it's filled up to 0.8. So let's say this is 0.8. This is water, right? And now let's label the dimensions. We have 0.8. This is our free surface. This would be 0.2. That's 0.2. Then this will be 1 meter, and we have a diameter of 0.5 meters. Okay, it says that the tank is accelerated vertically. Okay, so vertically, and since it's not saying if it's downward or upward, so let's say this is upward. Okay, so this is our acceleration, and the value is 6 meters per second squared. Okay, so we are asked to find the pressure at the bottom of the tank if it's having an acceleration of this value. Okay, so since we know the equation, okay, so let's just write apply the equation. So the equation is that delta P. Okay, so this is delta P. So delta P is just equal to the unit weight of the fluid, the water, times the delta Y times 1. Okay, since it is upward, this is plus, and since it is also accelerating, then this acceleration is plus AY all over G. Okay, so our reference is something like this point, okay, from point 1 to point 2. So our pressure here would be I can't draw if it's linear or not, okay, but you would have a, okay, let's just write instead point here, there's going to be a variation, but probably something like that. I'm not sure, but the point here is we have a greater pressure here at the bottom. Okay, so plus, because plus some value from this term, Okay, so the unit weight is 9.81. That's in kilonewton per meter cube times the delta y. So the delta y is just simply this one. So from this point to this bottom, that's 0 0.8. 0 0.8 meters. Okay, times 1 plus the acceleration, which is 6 meters. 6 meters divided by the 9.81, and the unit cancels out. Okay, so our delta p, or p at the bottom, okay, it's just simply, it's just 12.6, right? So 12.6 kPa. Okay, so again, if we review our steps, so we first sketch the problem, and we just apply the equation, because since we have this value already, the acceleration, and we have the delta y, we have the unit weight, we have the value of the g constant, so we can actually solve for the unknown, which is the pressure at the bottom. Okay, so that's the gauge pressure. Okay, and we just apply, we substitute all the values, and then we obtain this pressure, which is 12.6. Okay, so let's try, just for additional information, let's try to solve using hydrostatic equation only. So basically that would just be times the h, and the h would be 9.81 times 0.8. 9.81 times 0.8, that's 7.84 8 kPa. Okay, so we see that the pressure, if we don't consider the acceleration of the container or the vessels, it is lower than the pressure values if we consider the acceleration. Okay, so I guess in the next video we will start derivations and problems for the rotating motions. Alright, so see you in the next video.